Let's quickly go through a past homework problem. A solid circular bar of diameter d equals to 50 mm is twisted in a testing machine until the applied torque reaches the value T equals to 500 Nm. And this value of torque, a strain gauge oriented at 45 degrees to the axis of the bar, gives the reading of epsilon equals to 339 times 10 to the power minus 6. You are asked to determine the shear modulus of the material, the Young's modulus of the material by considering the stress element, as well as sketch the stress elements counterclockwise oriented at different angles. To determine the shear modulus of the material, conventionally we would like to consider some formula like tau equals to g gamma, right? Because we only know on this strain gauge there is an epsilon, but we don't know about gamma. However, there are a lot of information missing, but one thing we can utilize is the formula I just introduced to you. Still remember that for a 45-degree inclined element, there is no shear stress acting on it. Instead, there is axial stresses acting on this element. Still remember that for the positive torque, it is tensile in this direction, or it is compressive in this direction. Under this case, this stress element is under the maximum axial strain. Therefore, we can find the maximum shear strain inside this bar by using this strain gauge inclined at 45 degrees. Since the maximum axial strain measured by this 45-degree oriented strain gauge is given by 339 times 10 to the power minus 6, then the maximum shear strain is just twice of it, which is 678 times 10 to the power minus 6. Consider in the very first step, when we derive the torsional formula, we write the shear stress inside the bar in this form, that is the ratio of the shear stress to that of the maximum. Then the maximum shear stress can be written as G, the shear modulus, times the maximum shear strain, gamma max. And then you absorb this term into the row behind. Consequently, by integrating both sides, you can find the torque acting on this bar equals to the shear modulus times the maximum shear strain times the polar moment of inertia divided by its radius, where polar moment of inertia can be found easily by using this expression. Consequently, the shear modulus of this material, by substituting the numbers into it, is given by 30.04 gigapascals. Now, by using our information in part A, we can find the maximum shear stress inside this material, which is 20.37 million pascals. Consider this 45-degree inclined stress element. For the 45-degree inclined element, the maximum tensile stress acting on this is just the maximum shear stress, but you know it is just E times epsilon, E times the axial strain. By substituting the values into it, you can find the Young's modulus of the material is 60.09 gigapascals. You may observe that, wow, why? This number is just twice of the shear modulus. Well, it is just considering this inclined stress element, but it is left to you to think of why. Next, we need to sketch the stress element counterclockwise oriented at 22.5 degrees, 30 degrees, 45 degrees, and 60 degrees. Firstly, let's consider a 22.5 degrees counterclockwise oriented element, which is like this. For the positive torque, the shear stress is on the left hand side and the right hand side is like this. Therefore, we can say that the stresses on the two dominating surfaces is like this, and we can sketch the rest of them. Besides, since it is a positive torque, the direction of tensile axial stress is like this. Therefore, we can determine the direction of those two forces, the axial tensile stress on this stress element. Finally, we can draw the rest of them. As what we discussed in the previous special case session, for the 22.5 degree oriented element, the magnitude of all forces acting on this stress element is just the maximum shear stress divided by square root 2, which is 14.41 million pascals. So all stresses have the magnitude of 14.41 million pascals in this figure. For the 30-degree counterclockwise oriented element, first we determine the directions of the stresses on this stress element. For this element, it is just 30-degree oriented. The positive torque will generate the shear stress like this. Then we can draw the shear stress on the dominating surfaces, and we finish the rest of them. For positive torque, still the axial load is tensile in this direction. It is compressive in other directions. That's done. So we have determined the direction of all shear and the direct stresses on this stress element. The magnitude of the shear stress acting on it is 10.19 million-pascals, while the magnitude of all axial stresses is given by 17.64 million-pascals by using the equations we derived before. 45 degrees is a rather special case. In this case, there is no shear stress acting on it. There is only the axial stress, and as discussed before, for the positive torque, it is tensile in this direction, while it is compressive in this direction. All the stresses inside the spicula has a magnitude of 20.37 million-pascal. Talking about the 60-degree oriented stress element, originally the element looks like this, and when it is 60-degree oriented, it will be like this. On this stress element, for the positive torque, there were two shear stresses like this. Consequently, we can draw the shear stresses on the dominating surfaces, and we can finish the rest of the shear stresses. For the axial stress, similarly, for the positive torque, it will be positive in this direction and the negative in this direction. The magnitude of all shear stresses is given by 10.19 million-pascal, while the magnitude of all axial stresses is given by 17.64 million-pascals.